Welcome to Physics in Films. This is the grand opening on At Principles of Natural Philosophy YouTube channel. The videos in this series, entitled Physics in Films, will be motivated by the work of the Hollywood directors. Each video will be dedicated to a Fermi problem based on the scientific plot, or part of the plot, shown in one of the blockbuster Hollywood movies. The inaugural cinematographic Fermi problem will be based on the 1996 movie Independence Day. A victory worse than a Pyrrhic one. The two greatest enemies that the Romans ever faced were the Carthaginian Hannibal and the Greek Pyrrhus of Epirus. Pyrrhus has remained in history as one of the most important generals of antiquity. However, to most he is known from the phrase Pyrrhic victory. During his campaign in South Italy and Sicily to help the Greek city of Tarentum, Pyrrhus was able to defeat the Romans but suffered great losses in the battles of Heraclea in 280 BC and Asculum in 279 BC. Most of his army, his personal friends, and most important commanders were lost. In the section Life of Pyrrhus in Parallel Lives, Plutarch reports the general's reflection on the victories, which is usually summarized as, if we are victorious in one more battle with the Romans, we shall be utterly ruined. Indeed, without being able to replenish his human and material resources after a lost battle in 275 BC, he returned to Epirus. Hence, a Pyrrhic victory is a victory that comes with a devastating toll on the victor. However, it is still a victory on record. It appears impossible to imagine a game in which both sides lose when the rules require a winner to be declared, but Hollywood is never short of imagination and has been able to create such situations. Perhaps the term Hollywood victory should be coined for a victory in which the winner is also a loser of the game. Again, it appears impossible to happen, but wait until I finish the Fermi problem that I have in mind for Independence Day. In the movie, an advanced alien species arrives in the vicinity of Earth with an immense mothership. Smaller but still extremely big ships are then deployed above every major city on Earth, ready to obliterate humanity. However, humans discover the way to destroy these ships and drop them on the ground. Is this victory one worth celebrating for? Let's embark on a Fermi problem to decide. First, some data from the movie. The military reports that the mothership has a diameter of over 550 kilometers and a mass roughly 1/4 of the Moon. It releases several smaller, but still, immense ships that each measure 24 kilometers in diameter. Although we do not know the exact construction of mothership, using its data, we can compute the order of magnitude of its average density using the formula density equals mass over volume, where the volume is of order L cubed. The mass of the Moon is 7.3 times 10 to the power of 22 kilograms. Therefore, the order of magnitude of the mothership's density, as implied by the director's numbers, is between 10,000 and 10 million kilograms per cubic meter. This density is extremely large. Since most of the mothership is empty space, the actual material density is larger. For example, if the material occupies 1/10 of the volume, its density is between 100,000 and 100 million kilograms per cubic meter. To compare, the density of iron is 7,870 kilograms per cubic meter, and the density of aluminum is 2,700 kilograms per cubic meter. There will be no advanced civilization which is going to use a material which is at least 10 times denser than iron. If anything, the opposite is true. To propel a huge spaceship, an intelligent species will use an extremely strong, durable material with as low density as possible. I will be nice to the director, and I will ignore this inconvenient result. I will assume that the alien nanoscientists have invented a material which has the density of the water, just 1,000 kilograms per cubic meter. Now, let's compute the potential energy per deployed ship. Potential energy equals mass times acceleration of gravity. times hovering altitude. And since mass equals density times volume, the final formula is potential energy equals density times acceleration of gravity times volume times hovering altitude, where the acceleration of gravity is 10 meters per second square and the density as assumed previously. It remains to estimate the volume V of the ship and its hovering altitude h. The hovering altitude is relatively easy to estimate. The Empire State Building, with its antenna included, is 443 meters tall. Hence, very conservatively, the order of magnitude of the hovering altitude is 1,000 meters. To compute the ship's volume V, since we already know the radius of the base, we can either boldly compute it as the cube of the radius r, or attempt to be more precise by multiplying its base surface area s by its height L. To estimate the height of the ship, we need to rely on visual comparisons. Without being too sophisticated, we observe that, in one scene, an airplane flies across the vertical wall of the ship. Using this, the height must be at least 1,000 meters, which, in combination with the base area, gives that the volume of the ship is 10 to the power of 11 cubic meters. Assuming, once more, that 90% of the ship is empty space, our estimation has determined that the volume of the material is between 10 to the power of 10 to 10 to the power of 11 cubic meters. Inserting the values of ρ, g, v, and h in the potential energy formula, we find that the ship is storing an amount of energy between 10 to the power of 17 to 10 to the power of 18 joules. After the humans shut down the ship, the burning and exploding ship slowly starts to lose height and eventually hits the ground. Ignoring any internal explosions, its potential energy is not lost. It is released in the environment as heat. A fast release of a large amount of energy is an explosion. Hence, an explosion will occur. However, is this explosion severe or something like that of firework? Although the amount of the released energy is known, without having another well-understood quantity to compare, it is not easy to draw a conclusion about the severity. Towards this goal, let's use the Hiroshima bomb as a reference point. The Hiroshima bombing occurred on August 6, 1945, during the final stages of World War II. The bomb, nicknamed Little Boy, was dropped from a bomber and exploded approximately 600 meters above the city. The explosion instantly killed an estimated 70,000 to 80,000 people, with total deaths reaching over 140,000 by the end of the year due to injuries and radiation sickness. The city was largely destroyed, and the long-term effects included severe radiation-related illnesses and genetic damage among survivors. The yield of Little Boy was about 13 to 16 kilotons of TNT. 1 kiloton of TNT releases 4.2 times 10 to the power of 12 joules of energy. Therefore, the order of magnitude of the released energy in Hiroshima was 10 to the power of 14 joules. Did you really pay attention to the two results? The stored potential energy is 10 to the power of 17 to 10 to the power of 18 joules, while the Hiroshima bomb delivered 10 to the power of 14 joules. When the humans shut down the ship, they effectively release 1,000 to 10,000 Hiroshima bombs above the city. And this happens on every city on Earth. Yet, the movie shows us that there are still humans to celebrate the victory. The previous Fermi calculation reveals just one of the many misunderstandings of science in the movie. Additional serious issues exist with various other physical laws. Now that you have appreciated the magnitude of the ridiculousness in the original Independence Day, you could decide on your own how much worse everything became in the 2016 sequel Independence Day, Resurgence. So, what is the moral from our Fermi problem? In sci-fi movies, Hollywood directors usually present impressive sizes and numbers to instill fear and exaggerate the human's weakness against the enemy. However, by doing so, they have unintentionally acted against their own goals and have predetermined the outcome to be exactly the opposite of what they would really like to. This movie is by no means a unique example for such a scenario. Stay tuned to my channel for additional examples. I hope you liked this cinematographic Fermi problem. If you did, please subscribe to my channel to help the creation of more content like this. Thanks a lot for your support.